Hi, I'm Sivaram, founder and CEO Jaji Technologies. Today we are going to talk about soft sensors. What is soft sensor, how it works, what are the benefits, and what are the technologies that are used to build and deploy the soft sensors. So let's get started. So what is soft sensor? It is an AI/ML based model that basically predicts the product and intermediate product qualities using the process information like reactor temperature, reactor pressure, maybe column reflux ratio, kind of operating conditions. So it takes real-time data from the process using the DCS or PLC or SCADA kind of systems and then feed them to the AI/ML model and then predicts the product qualities. The product qualities are then written back to the DCS so that operators can see the real-time product qualities. So typically there are physical analyzers which are used for this purpose. However, they're very expensive. So many times we don't often see much number of analyzers in a process plant. They optimize, maybe they keep it one or two at a very critical sections. However, in most of the columns and reactors, there will not be any physical analyzers. So in order to guide the operator with the intermediate product qualities and final product qualities, the soft sensor will come very handy. So in the advent of the AI/ML technologies and the increased awareness of the AI/ML, now it becomes very, very useful. And it is also becomes very easy and quick to deploy the soft sensor in process industry. So let us first understand the process. There are two types of processes, linear and non-linear. So linear processes are like homogeneous. That means the behavior is same across operating conditions, and they follow the rule of superposition. That means the behavior of one variable, when is it added to the behavior of another variable, the resultant will be sum of those two. That kind of behavior is typically applicable for the linear process. However, in non-linear process, it won't applicable. It is not homogeneous. Depending on operating situation, condition, the behaviors keep changing. So the relationship between input variables and output variables typically is a product of complexity, and it may be logarithmic in nature. It may be of nonlinear in nature. So nonlinear models are very difficult to build and predict. So there is always certain unexpected error will come, in the model behavior. Let us understand what is steady state. So when an operator changes a set point of a furnace pressure or a feed ratio controller, the process takes some time to settle down. So it takes some time to reach the steady state where the response becomes flattened out. So during this process of reaching steady state, the process becomes dynamic. So the time that takes to reach the steady state after certain change is done by the operator is called time to steady state. So when we are building a soft sensor, typically a product quality versus operating conditions of the plant, so we should ensure that process is in steady state when we take the sample. Otherwise, when you take a sample during the dynamic condition, probably your model error will be more. Now let's understand what are the variables and variability. So for every soft sensor, there will be some input variables and there will be one output variable, which is product quality. The input variables are typically the process parameters which affects the quality directly or indirectly. So it is very important to select the right variables. If you don't know the right variables, you need to take many variables and try and see the relationship between variables and the product quality using maybe the correlation matrix or using the XY plots, then determine which are really depend, and then those variables have to be taken. So do not take more than 4 or 5 variables. I prefer 3 variables maximum you should take for soft sensor. So then what is variability? So the variability in the product quality has to be captured fully when you select the list of variables. So if you take same variables which are collinear, probably you may not capture all the variability. So select the variables which are not related, or you can say fairly independent, which can capture most of the variability in the product quality. So while building the AIML model for soft sensor, we have to make a choice on the algorithm. There are many algorithms available to build the model. For linear process, we can use regression or partial least square. For non-linear, we can use ANN and RNN models, algorithms. So you have to try a couple of algorithms and see what really fits well for that particular soft sensor. So it is kind of experience and trial and error things that help you to get the right algorithm. So let's talk about the benefits. As a soft sensor provides the real-time quality information right in the DCS or PLC or SCADA, the operators can move the input parameters in order to control the quality right on the spec. And by doing so, they can also minimize the quality giveaway while ensuring product is within the specification. And many times it can help reduce the sample frequency, reducing the load on the laboratory. And in some scenarios, you can also eliminate the need for expensive analyzer. Now let's talk about the myths. Many people think that soft sensors can replace completely the analyzers or lab sampling. Definitely not. It can only minimize the sampling frequency, as I told you earlier. So the accuracy also a factor that we need to consider. Most of the linear processes, we can create a models with a very good accuracy from 85% to 95% match to the lab data. Directionally, they give you very good indication where the process is going. However, it is very important to update the prediction with the lab data and ensure that the prediction is in line with the laboratory. So you have to regularly maintain the soft sensor by continuously checking with the laboratory. So there is something called auto lab update functionality where the model gets automatically corrected based on the feedback from the laboratory. So this is very, very important in order to ensure that the soft sensor is not drifting away from the laboratory values and eventually create problem to the process. So now let's see how to build the soft sensor. Many people use various technologies. Maybe people use Python and maybe readily available tools. So I'll be today showing you the example using insys.ai. It is an AI platform from Jaji Technologies. I myself worked as an advanced process control engineer and implemented about 25 to 30 projects across India and Middle East. So during those projects, I built numerous soft sensors using various technologies. So I'm very, having good experience or hands-on experience on building the soft sensors. So let's get started. So let's get started. So I've just opened insys.ai. So I can create a new model here. give a name. So what we're going to do, we're going to predict the column top purity. So we call it C101 column number. So let's give some name, C101 top purity, and then give some description. Or we can say soft sensor. And then in the model type, we can select parameter prediction. If we know the asset, we can link the asset from the asset framework. If we want to add some image, we can give some icon for this. Then save. The model project is created. Now we can view that. So here you can see the model details, data sets, input variables, and output variables. Let us first import a data set. So here in the top, you can see that these are the 6 steps we need to follow in order to build a soft sensor and publish online. So first step is to create a model project. Second is to import the data. So now the two ways you can import the data. Import the data directly from info view, which is already saved. So you can create an info view with a lot of input tags and the calculated tags, and then directly import the info view here. Otherwise, we can also create a new info view here, and then import the data. That means whatever the tag in our data historian, we can directly pull here into our project. For this example, I will use sample data in a CSV format. We can also import the data using comtrade format as well. So we'll just use CSV file for this example. Now, for batch information, we can also import from Insys batch database. But right now, let us go with the CSV file. So now we select the sample data. So distillation purity data. So I just imported this data. So we have few parameters here. I can click on this import. Now the data is imported into our project. So here I can see top pressure, top temperature, bottom temperature, recycle ratio, and we have top purity and bottom purity in this uh, data file. So we have data, everyday data at 00 hours. Now, on the left side, if you see, we can go to next step data analysis, and then we can select the variables first. So I can click on this plus button and then select uh, what are the inputs that I want to use for this model and what is my output, that is top purity. So if I know the tag name for this top pressure, when we want to deploy online, we want to link that top pressure to real top pressure. So I can give directly the tag name here. So I can give C101 top pressure here, right? Top pressure. Then I can give here C101 top temperature. And then here C101 bottom temperature. Then here we have C101 recycle ratio. For again, for the output, so let us say we are using NSYS limbs, or if you are using any other limbs, if that data is pushed to the historian, we can use that tag here. So what I will do here, I'll use the limbs tag here, right? So top purity. So here I'll use this limbs top purity as the tag, and bottom purity I don't have to worry, so I'll just leave it as a dummy tag, and then I can click on this save button. So what happened? These variables are selected. You can see that the input parameters, some statistics have been calculated, like median, average, min, max, standard deviation, CP, CPK for input and output. Now here you notice that there is a raw data and there is a sliced data. So we'll come to the slicing separately. Now, the next step here is to do some kind of variable analysis. So now we can see the trend line chart of this parameter. We can highlight and see how the variability of individual uh, you know uh, tags. Now we can also see multi-trend so that you can see independently those tags variability, and then you can also see XY plot. This is very useful in order to see the relationships. For example, here you can see uh, the relationship between top purity and top pressure, and then top temperature, and then the bottom temperature. So here we can see whether there is a linear relationship or not. If you want to alter this, x-axis, I can also select, let us say, top pressure here. So have, I can reverse the scale, like axis. Okay. And then you can see the correlation matrix between these variables. I can see there is a strong correlation between top purity and top temperature, which is 0.987, right? And then if you want, you can see SPC to see whether the data is in good shape or not. And if you want to do some kind of fast Fourier transformation, if it is an electrical signal, you can see harmonics, you can see the voltage analysis, voltage sag analysis, and the waveform analysis. All those things can be seen if you're bringing an electrical signal into the platform. For the moment, we'll just stick to these things only. Just look at these things only. So right now, I'll just leave it as it is. I don't. I mean, you can spend some time here, try to find out what are the points that may be deviating from the relationship so that we can mark them bad. Then move to data slicing. Now here, I can do auto slice. That means system will automatically identify based on some kind of analysis. So there is also anomaly detection algorithm available. Basically, I can select any tag, uh, you know, and then select some kind of algorithms like isolation fast, LSTM, and then we can run this. So it will take some time here. So what it does, it basically uh, checks the vector and find out any abnormal data points depending on the its own pattern. Basically, kind of autocorrelation probably. It may not be exactly autocorrelation, but kind of. But it does identify anomalies. So here it finds that these are the points which are anomalies. So I don't want to mark them bad at the moment. I just want to show you the scenario, why how the AI can predict the anomalies. Now, what I will do, I'll go to I'll use a standard auto slice mechanism. So what it does, it basically takes the identifies standard deviation and eliminate all the data which is above and below two standard deviations plus or minus the median. So that is pretty standard way of eliminating the outlier. So I use that thing. So I can set it as a bad vector here. Manually also I can select any slice here, and then I can right click and then mark them bad, or set some default values or make it interpolate. I can edit if you want. At the moment I'll just skip this, and then there can also be, I can also do event analysis. But right now let us stick to this uh, uh, small slice. Let's not go to event analysis at the moment. That's mainly useful for advanced pattern recognition. Now I can select some data sampling. I can use 70% of data for training and 30% for validation. Then here there's a variable finalization. Basically, I can use AI again to identify, uh, you know, parameters which are really useful for building a model. I mean, which are more effective. Here, I selected here, I think, one, two, three, four input parameters. So if you want to further, you know, reduce, you can use this, include variables. You can put three and then select final variables. At the moment, we'll stick to that. Okay. So right now I can specify, let us say, three here, and then I can, save it. Otherwise, I'll put four and then save it. Oh, you need to select the variables. Okay. Now it is running the algorithm. Since I said four, I think it will take finally all the four parameters. It's going to take some time because it's running the algorithm back and find out the real input variables, which can affect the uh, what do you say, more effect on the model, effect on the output variable. So it has selected everything because it's given all the scores five here. Okay. If I put three, probably it will eliminate one. Okay. Now I save this, and then we can also do multivariate analysis, but at the moment we'll not do that. Let's move on to the next step, model algorithms. So I have many algorithms here available: linear regression, partial least square, ANN, fast tree regression, random forest. So let's use the linear regression for classic thing. And again, you can use different trainers here. So let us start with the basic thing, just for demonstration purpose. And then I select this linear regression model, and then I can go and do the training. So now it fit the model. Now you see the R square is 0.9, which is pretty good, pretty good. So anything more than 0.95 is pretty good. Okay. At least the lowest that we prefer is zero point 0.9. In the worst cases, 0.85. So anything less than 0.85 is a red line. So don't use that model. Right. Then let's do the validation. Now you see there's a perfect, validation is done. Prediction versus actual. And here I can see the same thing in tabular view. And then I can also see the residual plots here. I see that. Uh, So prediction versus actual are also pretty good, and residuals are okay. So it looks like good model fit. So I can also do a real-time prediction. So what it does, it basically takes the input variables and try to predict. So there's some, I think I need to save the model. That's why I think this it's not showing here. So let me go to the next step. I need to build the model. Uh, so build it here, and then now here I can deploy directly to Insys process. I can send this to a KPI, or I can link this to a LIMS quality. So basically, whenever uh, somebody is taking a sample, immediately using this model, it can tell what's going to be the prediction, for that sample. Then they can do the lab update, lab analysis, and then system will compare those values. Okay, take for feedback. And I can also export the model as zip file or as a ONNX model. So it can be imported into third-party uh, platforms where they can use this model. So for this example, I will not do that. I will try to go for in our own system. I'll try to uh, deploy it online. Now you see that if you want to deploy online, I can use the Insys AI online. So I can just keep it online and then turn it on, and then I can say predict every 1 minute, and then enable prediction. I can give a prediction output. So this is a manual input tag, so I'm just saving it. So here these are the input tags which we have already selected, so I don't have to change anything here. I save it. So that means now this model is deployed. That is, then view online. So now you see that uh, these are the input values. This is the prediction. These are the data when it was last executed. So as simple as that. So NSYS AI helps you to import data directly from NSYS or from the files, and then create the model, and then directly deploy it in NSYS AI online. Or you can also export the model so that you can use third-party systems to deploy the model. So it's a very, very powerful, intuitive, user-friendly self-service platform for building the soft sensors. So we have come a long way. We have learned what is soft sensor, how it works, underlying technologies and methods and algorithms, platforms, and we've seen how to build it and deploy it using insys.ai. Now, to conclude the session, in order to effectively control the quality, you need to have the soft sensors, or rather, I would say, soft sensor comes very handy to effectively control the product quality. And the accuracy of the soft sensor depends on the how good quality you have, how nicely the model is built by the chemical engineers or data scientists, and continuous lab update is important for ensuring that the predictions does not drift away from the lab data. Thank you for your valuable time, and if you have any doubts, any clarifications required, or any suggestions, please comment on this video. Thank you very much for your valuable time. Thank you.